Okay, hi class. We're looking at starting into quadratics with lesson 3 of chapter 1. This one's called maximum and minimum. So we're really trying to find lowest and highest points on a parabola. That would be the vertex. And before we do that, we really need to be able to answer some questions from grade 10. So I'm just going to give a sort of a survey of questions that you should have encountered in grade 10. You may not have kind of mastered all of these concepts, but just looking at the list here, you've got the different forms of a quadratic function. There are standard form, vertex form. In vertex form, there's also the reading of the coordinates of the vertex, determining if it's a maximum or a minimum from the appearance of the equation. There's also, of course, the symmetry property of parabolas, which is revealed by the axis of symmetry. It's a vertical line that divides the parabola into two equal halves and also passes through the vertex. Common factoring, and then looking at polynomials. Perfect square is specifically important to the method of completing the square, and we need to know the pattern before we do that. Of course, there's also simple and complex trinomials, terms you've seen before. So we're going to look at some of the just overviews of content from grade 10 just quickly before I look at some examples from the prerequisite skills handout. Okay, here's a slide I used before in grade 10 for my students to understand special products. So before we can get really good at factoring, we need to know how to expand. So in this table, there's a lot of information here. First column has the binomial product. Okay, so that's the multiplication of two binomials. The second column is showing the distribution steps. That's the expansion of the binomial. Then there's the simplified expansion with like terms collected, and then the number of terms in the simplified expansion is also summarized. So if we look at the first section, the square of a sum, so we're adding terms in a binomial, and the pattern here, if we look at a plus b, we would get 4 terms as follows using the FOIL distributive property. When that is collected, we have 2ab's. That would be 3 terms. X plus 7 all squared. Again, that's going to produce 2 identical middle terms. 7x doubled would be 14x. And then, of course, at the beginning and the end, we have the square of x and the square of 7. So we get a predictable pattern there. For something where binomial has coefficients on both parts of the binomial, that would produce perhaps the most complicated sum of square pattern, where we have, again, first and last terms would be the square of the first and the square of the last, and the middle terms are identical, and the simplified expansion would have double that middle term, so that would give us 120 x's. In all 3 cases, there are 3 terms. Okay, we look at the square of a difference. This is just with subtraction in between the parts of the binomial. Okay, just note in the tip here that a subtract b is equivalent to a plus negative b. So when we examine the first row here of this category, we find that we get, as before, 2 middle terms which are identical, and the end terms here are also the square of the first and the last. And notice the sign here is unaffected by the subtraction. We're still going to get the square of b and the square of a at the beginning. Okay. Now here, all right, I also just caught a mistake there, so I'm just making a change to the table there. So for the first square of a difference, we have 3 terms again, twice the middle term except with subtraction, and then the square of b as well. Next row, we see similar pattern developing here. Notice that it simplifies to negative 2xy and then plus y squared. And finally, when we have 8 and 9 as numerical values for our terms here, something where the first term has a coefficient other than 1, we would produce the square of 8x, which is 64x squared, and the square of 9, which is 81, with 2 terms that are 8 times 9 times x, which would be twice 72x, and in that case, of course, there's 3 terms as well. We look at the sum and difference of a binomial. So here it's a plus b times a subtract b. So these are called conjugates. So a plus b is the conjugate of a subtract b. In this case, the FOIL, or distributive step here, is going to produce 2 middle terms which have opposite signs. And of course, when we add them, those terms will produce 0, or they'll cancel out. So we only have 2 terms for a difference of squares here. This is called the difference of squares, as you can see, because it's subtraction between two squared terms. So this is, again, the product of a sum and a difference. The next one here also follows the same pattern here, no middle term. Last one is going to be the most complicated of the three, but it would be still the square of 6x and the square of 5, except in this case, with the sum and a difference, we will have subtraction between the terms. And of course, these all have two terms. So that's just a review of expansion. Okay, quick review of common factoring. If you care to just examine this portion of the video here, common factors, of course, are looking at the highest multiple of, or highest factor of a given number of terms. So in this case, we say remove the common factor, and at that point, the expression is said to be factored. So an example here, the definition, a little more detail, is when you can no longer remove variable factors and no more integer factors can be removed except 1 or -1. It's said to be completely factored. So 2x plus 4 can be factored. Common factor, of course, is examined by looking at the factors of each term. Right, so here clearly 2 is the only factor common to both, so we would say that 2x plus 4 factored would be 2 multiplied by x plus 2. So that's pretty simple. Looking at slightly more complicated common factoring, we've got the definition of factoring again here as a reverse of expansion. And factoring restores a polynomial to its product or factored form. So if we were to look at something beyond greatest common factor, well, we have for multiple terms, possibly containing a variable as well. And we can also use common factoring when a binomial is actually the greatest common factor. So here we have two terms here, and then x plus 2 would be common to both x and -4. And so that's a strategy which we will often use with complex trinomial factoring. Here again, where we have groups of terms or pairs which on their own have something common, but maybe as a whole set don't, we can factor them in groups. So here, the first two terms have C common to them, and the last two terms have D, and then that reveals a new common factor, A plus B. Factoring, of course, can always be checked by expanding the resulting product using the distributive property. All right, let's look at factoring simple trinomials. So here we have a simple trinomial. X plus 3 times x plus 2 is the factored form. Let's see how we would arrive at that from the expanded form. So first, when we expand it, we notice, of course, the pattern as we've seen before. We have 3 times 2 and 3 plus 2 in the middle. And so if we were to stop right there, we could see that if we could freeze it in that form before it was simplified, we would obviously know what the numerical values were in the factors. It would be 3 and 2, both positive. Okay, but when it's in the form as we see here, where we have 5x and 6, after the simplification, it's harder to see. But what we can do is pattern this in reverse and know that we've added 2 terms to get 5 and we've multiplied 2 terms to get 6. So we could reverse the process and, of course, determine that 2 and 3 satisfy both requirements. If we were to factor this one, looking at 2 numbers that add to 7 and multiply to 10 would, of course, be 5 and 2. So we have that list option, which we can use if we're not certain of the 2 values right away. We can make an exhaustive list of all the factors of 10, and then look for those which add to the middle term, which would be 7. And so 2 and 5 are the candidates. The order is non-important here. Whether we put x plus 5 first or second, it's still going to produce the same result because multiplication has the commutative property. The order does not affect the outcome. Okay, and again, the check here is shown as just a verification that it's been correctly factored. All right, this page here is just a quick proof of why factorization of x squared plus bx plus c requires, in general, 2 numbers that multiply to c and add to b. Some of you may be interested in sort of the proof side of math. If you care to, just pause the video and have a look at it. Otherwise, you can continue on with the next section, which would be factoring complex trinomials. All right, so a complex trinomial by definition has a leading coefficient on the x squared term not equal to 1. We can always try guess and check as a strategy for factoring. There's nothing wrong with that. It's at some point it becomes a little bit too time consuming, but just to show you the method, say you take a trinomial and you're not sure about the factors, but you figure you can make it work by patterning here. So you know that, okay, well, to get 3x squared, it'd have to have two numbers which would multiply, and both have to have an x in them. So one of them would have to have a 3 as a coefficient, the other one could have 1. So that gives us something looking like this. Now all we have to do is figure out the last two terms, which multiply to -2. And of course, the factors of -2 are very limited. It's just -1 and 2 or -2 and 1. Which order would produce the middle term of -5? So I think you'd probably see that we're going to need -2 over here, and we're going to need +1 over here. And that would give us a factor of -6x. When we add 1x to that, we'll get -5x, and then the 1 and the -2 would produce a factor of -2. So that's a strategy which can be useful when you're not sure. Okay, the most common method for factoring complex trinomials is the method of decomposition. So the decomposition refers to the breaking up of the middle term into two parts. And these two parts sort of come from the step before the like terms were collected. So we're almost recreating the expansion process. Okay, so what we do here is we break up 11x, and we do it in such a way that we'll have two terms, both have x in them, and the coefficients on those need to multiply to give 24. Okay, that comes from 2 times 12. They also need to add to give 11. Well, obviously they need to add to give 11 because they came from 11x. So we can look at all the factors of 24, okay, which are, that's better to start with the factors than the sums, okay, because there's too many ways of adding to 11, but there are very few ways of multiplying to 24. So they're all listed here. And we look at the sum of those numbers. Now, in this case, they're all positive values. So 25 is a possible sum, 14, and then we get 11. Okay, so 8 and 3 have to be our two terms. So then what we do is we take our middle term, break it up into 8x and 3x. The order here, again, doesn't matter, fortunately, because when we look at how we would have expanded, we could change the order of the two binomials, and that would give the 8x and 3x in reverse. So here we could put them as follows, and then we group them. Brackets around them here is just to assist us in seeing that those are now associated. Got to remember that we still have addition between those four terms. And then we remove common factors. So we common factor out 2x from the first two terms and 3 from the last two. And then we notice, oh, look, at x plus 4 is common to both. And so if we recall common factoring with a binomial factor, we can now remove x plus 4 from both 2x and 3, and that produces the final step. Again, a check there to verify that that is in fact the factored form of our trinomial. Notice again here the factor with 2x is shown second, and that does not affect our outcome. So I'm returning to the prerequisite skills portion here. We have a worksheet, Blackline Master, which you probably have not received, but very similar to the questions on pages 2 and 3. The first section here called graphs and lines. I should be familiar with that by now, having done a review at the beginning of the year. Working with polynomials, we have maybe interested in knowing how to do questions 7, 8, and 10. Number 6, I've demonstrated the expansion sufficiently in the review slide. So if we look at number 7, here factoring completely the following. Okay, you may notice the patterning in A. The last term is the square of 1, and double that is 2, but of course it's -2, so it would have to be, this would be an example of the square of a difference. And if we look at B, this is just adding to 1 and multiplying to -20, so the positive number has to be bigger. In C, at first it looks like a complex trinomial, but I would have you look carefully and notice that 3, 3, and -6 are all common factorable. So that finishes up with a common factor of 3 producing a simple trinomial which is easily factored. Now D also, of course, here has a common factor to the three terms. So first, before we go ahead with the decomposition, we should try to factor out 2 from all three terms. Okay, so having done that, notice I actually removed -2 as a common factor. No problem there. I prefer to have a positive leading coefficient on my x squared term in the brackets. So just be careful with your arithmetic there. -2 times +4 is -8x. -2 multiplied by -3 is +6. So my next step is to decompose 4x into 6 subtract 2 x's, and that is to achieve a product of 4 multiplied by -3. So here, once that's done, we can see the next step would be to common factor our groups. Notice I've just slightly modified my brackets. I'm using square brackets in the first common factoring step, anticipating the use of round brackets in my decomposition step. So in this third line, you'll notice I'm taking 2x out of the first two terms, and I'm just removing -1 as a common factor of the last two. Now, if you think that +1 is a common factor, you'll discover that that's not going to produce two identical binomial factors. So looking at -2x and -3, obviously -1 is the most obvious common factor, although +1 would work too. But in this case, trial and error will work out the use of the correct common factor. And at this point now we're examining so the square root of 4n squared is 2n, and the square root of 1 is either +1 or -1, and -1 is the better fit here because the middle term is negative. So here half of -4n is -2, and if we look at the expansion, we're going to have -2n and -2n repeated, and then the square of -1 is +1, and the square of 2n is 4n squared. So that's a perfect square. C, as I mentioned before, is also a perfect square, which would follow the form x plus 4 all squared, producing x plus 4 times x plus 4. And of course, if we were to expand that, it would be x squared plus 4x plus 4x plus 16. So we can see there that when we have a perfect square, we have two identical terms which are half of the square root of the last number. So that's a pattern you want to pick up on for the completing the square method. Okay, I'm just going to quickly wrap up here by returning to this first sheet here. So the review topics here, it's really focusing on second degree relations, which are quadratic. The different skills involved are really going to be important. So I'm going to emphasize that you spend lots of time practicing this, and you have to be very good at factoring before you're going to attempt the method of completing the square, which you have done in grade 10. We'll do a little bit of work with gizmos just to reinforce the idea of the factorization of simple and complex trinomials in class, and then we'll look at even deriving the quadratic formula, which uses the method of completing the square. So be prepared for lesson 3, having looked at this content, and we'll look at two main methods in section 3, the method of partial factoring and the method of completing the square. Take care.